In this video, I'd like to talk about the math question of the day for April 2nd, 2023. And with this problem, we have that a manufacturer needs to make a cylindrical can that will hold 1.5 liters of liquid. Determine the dimensions of the can that will minimize the amount of material used in its construction. So to answer a question like this, our clue is that we need to minimize this. We will need the tools of calculus. This is an optimization problem. So go ahead and pause the video, see if you can work through this on your own, and when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through it. And if you do have suggestions for future questions of the day, feel free to leave those as comments. And like I mentioned, because we need to minimize the dimensions, we will need to use calculus. This is an optimization problem. But before we really start, let's just draw a quick sketch of what we're dealing with here. We have a cylindrical can, or a cylinder. So we will have circular tops and bottoms. And let me draw the rest of it very quickly. And with this cylinder, we are told that it needs to hold 1.5 liters of liquid. So this is the volume that it must hold. And since it's in liters, we will need to convert that to centimeters, or specifically cubic centimeters. Since 1 liter is equivalent to 1,000 cubic centimeters, and the dimensions of our cylinder, we will use centimeters for that. So we will need the radius of the top and the bottom. It will be the same in both of those. And we will also need the height of the cylinder. And we know that the formula for the volume of a cylinder is the area of the base multiplied by the height. And the area of the base, since it's a circle, would just be pi multiplied by the radius squared. And all of that will be multiplied by the height. And like the problem mentions, this is equal to 1.5 liters, or if we put it in terms of cubic centimeters, so that we can get R and H in terms of centimeters, then this will be 1,500 cubic centimeters for the volume. And this right here, this is what we call the constraint. This is what will limit our minimization of the amount of material that we'll use. And to determine the amount of material that we need to use, we'll need to consider the surface area of this. And remember that with a cylinder, you can imagine cutting it along this height here. And if we do that, we can imagine opening this up. First, we can ignore the top and the bottom. We'll come back to those later. But let's just focus on the body of the cylinder. If we cut it along a straight line up, then this will unfold into a rectangle where this length here, this is still the height, but this length along the top and the bottom, this would be the circumference of this cylinder, of the top or the bottom of the cylinder. And we know the circumference of a circle with radius r is just 2 pi r. So we can say that the surface area, or the area, is this surface area of the body of the cylinder, which is just this rectangle. It's 2 pi r multiplied by h. And then we need to add the surface area of the top and the bottom faces. But each of these is just pi multiplied by the radius squared. So we have 2 of those. We have 2 pi r squared. And this equation here, this is what we need to optimize or minimize in this specific case. And remember, with minimizing or maximizing a function, we will essentially just take its derivative and set that equal to 0. We will come back to that later, but before we get to that, we need to reduce this equation to an equation with just one variable so that we can actually take its derivative. And the way to do that is to use our constraint, since we know that this 1,500 cubic centimeters is just equal to pi multiplied by the radius squared multiplied by the height. And it looks like if we solve this for h, we can avoid taking a square root here. And solving it for h, we're just dividing both sides by pi r squared. We have that h is 1500 over pi r squared. And from here, we can just plug in this value for h into our area function, so that our new area function, which we can just call that a, this would be 2 pi r multiplied by h, which is this expression, 1500 divided by pi r squared. And we will add 2 pi r squared to that. And from here, we can start simplifying, so that our area is twice 1500, that's 3000. And the pi's will cancel. One of the r's will cancel, so we still have an r in the denominator. And then we get 2 pi r squared that we're going to add to that. So this is our area function. And let's rewrite it as 3000 multiplied by r to the minus 1 power. And the reason that we want to do that is it's easier to take the derivative of this. And like I mentioned before, to minimize or maximize a function, we need to take the function's derivative. Since if we have some general function, let's say that this is f of x, some continuous function, when we want to find its maximum or minimum points, we will take its derivative and set it equal to 0 to find what are known as the critical points, these x values that lead to these maximums or minimums. And that just comes from the fact that the derivative tells us what the steepness of the curve is at a given point. Specifically, if we look at the line that is tangent to the curve at a given point, the derivative will just tell us the slope of that line. So at a maximum or a minimum, notice that the line tangent to that point has a slope equal to 0. Or in other words, the derivative is equal to 0 there. So let's find the derivative of this, and we're taking the derivative of our area function now with respect to the radius r. Since we did eliminate h, it is now just a function of one variable. And using the power rule, we bring down the minus 1. We have minus 3000 multiplied by r to the minus 2. We just subtract 1 in the exponent. And we do the same thing for this term here. We bring down the 2. Now we have 4 multiplied by pi multiplied by that radius. And like I mentioned, we will set this derivative equal to 0 and solve that. So let's make some room to work on that. And we need to solve this for r. So let's add this term to the other side, so that we get 4 pi r is equal to 3000, positive 3000 over r squared. We will multiply each side of the equation by r squared, so that we can cancel out this denominator here. We'll just have 3000. And over here we have 4 pi r cubed. Let's divide everything by 4 pi, so that we have 3000 over 4 pi. And we can take a cubed root of everything while also simplifying this. This would just be 750 divided by pi. So we found the r value that should minimize this function. And if we want, we can even plug this into a calculator to get a decimal approximation. And when doing so, we will get approximately 6.2035, or we can just leave it as 6.20. Though going back to the original problem, we need all the dimensions that will minimize the material. So we also need h, and we know h is this quantity, the 1500. Let me set this right here. H is the 1500 over pi r squared. And if we plug in this value for r, we'll find that h is approximately 12.40700. So we can say 1 here for the decimal. So we have our dimensions, but we do need to be careful, since when finding the critical points, and we only found 1 in this case, we need to be certain that this actually produces a minimum value and not a maximum value. Since remember that with our general function here, the critical points can find either the maximum or the minimum value, since in both of those cases, that's where the slope of the tangent line is 0, or the derivative is 0. And the way to tell if we're dealing with a maximum or a minimum is to look at the second derivative. So we will need to take our derivative and find the second derivative by taking the derivative of this, the first derivative, with respect to r. So now we have the derivative of a with respect to r, and I should mention this is the second derivative of a with respect to r. We will ignore this equal to 0 now. We're just looking at this function for the first derivative. We will again use the power rule, and if we bring down the -2, this becomes 6,000, and we subtract 1 from the exponent, so we have r to the -3 power, and we bring down the 1 so that we get 4 pi multiplied by r to the 0, but that's just 1, so now we have this constant here. And the reason that we're taking the second derivative, if we go back to our general function here, the second derivative tells us how the derivative is changing. So we can look at the slope of these tangent lines as the x value increases. And notice that with a maximum, the slope, it goes from a positive value to 0 to a negative value. So for a maximum point, we would say that the rate of change of the derivative is negative. It is decreasing, meaning that the second derivative is negative. But with a minimum value, notice that the slope of the tangent line starts negative, then goes to 0, and then gets more and more positive. So here, for a minimum, we could say that the second derivative is positive. So let's go back to our second derivative. We need the case when this second derivative is a positive value. And let's just rewrite this as 6,000 divided by r to the third power plus 4 pi. And this is always positive, since r, the radius of the cylinder on the top and the bottom, that has to be a positive number. It can't be 0, or else it won't actually be a cylinder. And it can't be a negative number because we're talking about a physical radius. So this term is always positive because r is positive, and this is a constant, but it's a positive constant. So this is always positive, and therefore the second derivative is always positive, which tells us that the r value we found, that critical point, this value right here, was indeed a minimum value for the surface area of that cylinder. And with this r value, we're able to find the h value. And with that, we have the dimensions that minimize this cylinder.